Welcome to Module 7, Topic 7.2, Sources of Data, Experimental and Observational Data. By the end of Topic 2, participants should be able to distinguish again between different data types, identify key study terminologies, and define the differences between experimental and observational study data. To reintroduce some basic terminology, variables are characteristics of individuals in the population which vary across these individuals. An observation represents the actual value of that variable for a given individual. For example, age is a variable in a data set, and each individual person's value for age is an observation. Observations are stored in a matrix format where rows represent individuals and their associated observations, and columns represent variables with each observation of that variable in the sample. As an example, a survey was conducted with students in an introductory statistics course. Here are a few of the questions on the survey and the corresponding variables associated with each. The variable gender is each student's response to the question, "What is your gender?" The variable sleep contains each student's reported average hours of sleep a night, and so on. You can see that some variables have responses that are numeric, like sleep, or countries, and some have categories of responses, like gender. You can see here an example of a data matrix with variables in the columns and observations of individuals in the rows. There are several types of variables. A variable can be numerical or numeric, which can be broken down into continuous or discrete subtypes. Continuous variables have an infinite number of possible values, while discrete variables are counts or integers. Categorical variables can be broken down into nominal or ordinal subtypes. Nominal variables are categories without any order, and ordinal variables have an inherent order to the categories. Numeric variables can be subjected to algebraic operations like addition, division, and so on. There will be more detail on types of data and how we summarize each in Topic 7.3. In our statistics student dataset, we have gender as a categorical variable. It can take on one of a few distinct and mutually exclusive values. Sleep is numeric and continuous. That is, you can measure sleep out to several decimal points on a scale of time. Bedtime is a categorical ordinal variable. It is ordinal because there is an order to the bedtimes. That is, a bedtime of 10 p.m. to 12 a.m. comes before midnight to 2 a.m. Countries is a numerical and discrete variable. Discrete variables are made up of counts, and this is a count of the number of countries the student has visited. You cannot visit half a country, right? Dread is a variable that is categorical and ordinal because you are being asked to rank your level of dread with being in a statistics course on a scale of 1 to 5. You can also evaluate dread as a numeric variable. Ask yourself, what type of variable is the number of walk-ins to an emergency room on one day, July 4th? This is a numeric discrete variable. It is a number, but it is a count. Again, you cannot have 1/2 or 1/4 of a walk-in. It can only be an integer. Another exercise. We have data from an experiment evaluating the effectiveness of a new drug in reducing the number of migraines in a person. The data matrix contains a group variable that indicates whether the person is in the experiment group, treatment, or the control group, control. The variable num_migraines indicates the number of migraines each individual gets during a 3-month period. How would you classify each variable? Is each one categorical or numeric, and which subtype? Take a moment to think about this. The group variable is categorical and nominal. There are 2 groups, treatment and control, but they don't have an inherent order to them. The number of migraines variable is a discrete numerical variable because it is a count of how many migraines a person had in 3 months. We are often interested in the relationship between 2 or more variables, such as between access to healthy foods and a child having a healthy weight, or between smoking and heart disease, or drinking coffee and how tired you are. Summary statistics and graphs are useful tools to explore the data and relationships. In this example of a scatter plot, where the hours of study per week are on the bottom x-axis and the student's grade point average, or GPA, are on the y-axis, does there appear to be a relationship between the hours of study per week and the grade point average, or GPA, of students? Do you see anything unusual about any of the data points? There are a few outliers, or points that seem more extreme than the others. When we visualize data in this way, it helps us to think of the underlying reason for some of the relationships. It might make sense here that those who are studying 60 or 70 hours a week have high GPAs, but there are also those who study very little and have high GPAs. However, you don't see those who study many hours a week getting low GPAs. One student falls above the GPA maximum of 4.0. This might be an error in data collection, and as a researcher, I would return to how that data point was recorded and double check it. We'll discuss more on data cleaning in topic 7.4 and data visualization in topic 7.5. 2 variables are said to be associated if they show some connection with one another. A positive association occurs when observations with higher values in one variable tend to have higher values in the other variable as well. Negative associations are observed when observations with higher values in one variable tend to correspond to lower values in the other variable. If 2 variables are not associated, that is, there is no evident connection between the 2, they are said to be independent. Variables can be associated or independent, but not both. Another practice question. Based on what we've just learned regarding positive and negative associations and independence, and looking at the scatter plot, which of the following statements is correct about the head length and skull width of opossums? Now, I realized in reading this slide that opossum are marsupials only found in the Americas, so I put a photo in of this mama and baby opossum as a reference for head shape and for cuteness. Looking at the scatter plot, would you say that A, there is no relationship between head length and skull width, that is, the variables are independent? B, head length and skull width are positively associated? C, head length and skull width are negatively associated? D, a longer head causes the skull to be wider? Or E, a wider skull causes the head to be longer? The correct answer is B, head length and skull with are positively associated, which we can see by the grouping of data points in the scatter plot. Now, it's possible that either D or E are also true, but we cannot infer causality from an association. So we choose statement B because it does not imply causality, only association. When we suspect one variable might causally affect another, we label that variable the explanatory variable, and the affected variable is the response variable. But note that the act of labeling variables this way does not guarantee that a causal relationship exists. You will need to conduct analysis to determine the relationship. There are two primary types of data collection: observational studies and experiments. We've discussed both of these types in Module 6, so this is likely a review, but an important review. In observational studies, a researcher collects information from surveys, medical records, and may follow a cohort over time, and can find associations between variables. In experiments, a researcher assigns participants into groups for the explanatory variables, typically at least one treatment group and at least one control group, and follows participants over time. This assignment of the explanatory variable is needed to make causal associations. Just remember that association does not equal or imply causation, and causation can only be inferred from randomized experiments. Now we'll talk more about observational studies and sampling strategies. Each research question refers to a target population. It's often too expensive and difficult to gather information from an entire population. For example, if we wanted to know if a new drug reduces the number of deaths in patients with severe heart disease, we couldn't collect data for every case in a population. Instead, a sample is taken of a subset, a fraction of the population. We often hear anecdotal evidence like, "My friend's dad had a heart attack and died after they gave him a new heart disease drug, so the drug must not work." This is technically based on data and might be true, but it is a sample size of 1, which is really a single case study, and this case may not be representative of the population. Therefore, we cannot draw conclusions about a population from one case. In another example, if you're interested in whether people can become better, more efficient runners on their own just by running more, your population of interest is people. That's all people. Say that we test this hypothesis in a sample of a group of adult women who recently joined a running group. Who can we then generalize our results to? Only to adult women, but not even all adult women, because this isn't a random sample. This was a convenient group of healthy women in their 20s and 30s who were normal weight and were completely new to running. So our results are not generalizable enough to be a featured article that determines how everyone can become more efficient runners. Isn't it better to just include everyone? This is called a census, but there are many problems with taking a census. It can be very difficult to complete. There will always be people who are difficult to find or to reach, and typically they are people who have certain characteristics that distinguish them from the rest of the population, so we don't want to miss them. Populations rarely stand still. They are dynamic and change constantly, so it's never possible to get a perfect measure. It's more complex than sampling and certainly more expensive. In observational studies, researchers collect data in a way that does not directly interfere with how the data arise. That is, the researcher does not explicitly apply a treatment. Therefore, the results of an observational study can generally only be used to establish an association between the explanatory and response variables. Confounding variables are typically present in observational studies. These are variables that are correlated with both the exposure and the response variable. An example is that you might see an association between the use of sunscreen and skin cancer. But the reality is that sun exposure is confounding this relationship. If you are using sunscreen, you are likely doing so because you will have sun exposure, and sun exposure is in the causal pathway to many skin cancers. A prospective study identifies individuals and collects information as events unfold, such as in the Nurses' Health Study, which has been recruiting registered nurses and collecting data from them and their descendants using questionnaires since 1976. Retrospective studies collect data after events have taken place, such as when researchers review past events in medical records. Obtaining good samples is imperative to rigorous research. Almost all statistical methods are based on the notion of implied randomness. If observational data are not collected in a random framework from a population, these statistical methods, the estimates and errors associated with the estimates, are not reliable. The most common random sampling techniques are simple, stratified, and cluster sampling. In simple random sampling, or SRS, we randomly select cases from the population where there is no implied connection between the points that are selected. In this graphic, all of the dots are the population, and the red dots are the individuals selected for the sample. There are limitations, however. This still does not guarantee a perfect sample. A subgroup of the population could be left out of the obtained sample just by chance, and it may be expensive to conduct. In stratified sampling, we break the population into strata or groups of individuals or observations who are similar based on some specific characteristic or characteristics. We then sample from each stratum using a simple random sampling scheme. Strata are usually formed based on immutable or unchangeable characteristics at the time of the study of the individuals. Example, race can be a strata, or age group, or gender. The limitation is that analyses are more complex than in simple random sampling. In cluster sampling, clusters are a form of group determined by mutable or changeable characteristics, like geographic location, hospital, school, and so on. Clusters are typically not homogeneous, so we can take a simple random sample of clusters and then sample all observations or individuals within that cluster. This is usually a preferred method for economic reasons. Limitations can be that a cluster may be too large or difficult to identify or partner with, and that more advanced statistical methods are needed to analyze the data. In multi-stage sampling, we take a simple random sample of clusters and then take a simple random sample of observations from the sampled clusters. This is useful when clusters are large or if you want to have an even more representative sample. The limitation is the same for previous cluster sampling. If not properly done, the sample obtained can be subjected to bias and may also bias our results. Here we review some biases: non-response bias, voluntary response bias, and convenience sample bias. Non-response bias occurs when only a fraction of the randomly sampled individuals actually respond to and participate in the study, and your sample is no longer representative of the population. Typically, this is because the non-responders are different in some way that is important to your study results. Similarly, voluntary response occurs when the sample consists of people who volunteer to respond. Volunteers are often either healthier than the general population, or they have some personal investment our opinions or feelings about the subject matter of study. Either way, this sample will not represent the population. Inconvenient samples tend to include people who are easily accessible, like our example of the women's running group. All of these will lead to your sample not being properly representative of the population. Next, we'll review experiments. In experiments, researchers assign the participants to the treatment. If this assignment is done randomly, we have a randomized experiment. Randomized experiments are fundamentally important to show a causal relationship between two variables. There are 4 core principles of experimental design: control, randomize, replicate, and block. Control refers to controlling the study environment carefully so that outcomes can be attributed to the treatment, and also refers to using a control group. Randomize refers to both a random population sample and to random assignment to treatment and control groups. Replication is important to contribute to causal determination. Replicate the entire study in different environments or by different researchers, and within a study, replicate by collecting a sufficiently large sample. Block is essentially stratifying participants in your study. If there are variables that are known or suspected to affect the response variable, group subjects into blocks based on these variables, and then randomize cases within each block to treatment groups. The difference between blocking and explanatory variables is that explanatory variables or factors are conditions we can impose on our study participants, while blocking variables are immutable characteristics that the participants come with, but that we like to control for in our study. Again, blocking is like stratifying, except it is used in experimental settings when randomly assigning as opposed to sampling. You can also stratify in analysis, but blocking leads to a more representative experiment, and you may not have representative groups to stratify in analysis without it. An example, we would like to design an experiment to investigate whether energy gels make you run faster. The treatment group gets an energy gel, and the control group gets no energy gel. We suspect that energy gels might affect professional or pro and amateur athletes differently. Therefore, we block for professional status. We divide the sample into pro and amateur groups, and we randomly assign pro athletes to treatment and control groups. We then randomly assign amateur athletes to the treatment and control groups. Pro and amateur status is equally represented in the resulting treatment and control groups. Why is this important? Are there potentially other things to look for? Think about these on your own or discuss with others. You can do this practice question on your own as well, or discuss with a group, and then click to the next slide to see the answer. A study is designed to test the effect of light level and noise level on exam performance of students. The researcher also believes that light and noise levels might have different effects on males and females, so wants to make sure both genders are equally represented in each group. Which of the statements here is correct? A, there are 3 explanatory variables, light, noise, and gender, and 1 response variable, performance. B, there are 2 explanatory variables, light and noise, 1 blocking variable, gender, and 1 response variable, exam performance. C, there is 1 explanatory variable, gender, and 3 response variables, light, noise, and exam performance. Or D, there are 2 blocking variables, light and noise, 1 explanatory variable, gender, and 1 response variable, exam performance. You'll see that there are 2 explanatory variables, light and noise, 1 blocking variable, which is gender, and one response variable, exam performance. Finally, a reminder that random assignment and random sampling are two distinct methods which, when combined, are very powerful for helping to establish causation over correlation. In an ideal experiment, represented in the upper left-hand corner, we would have random sampling, as you see in our top row, and random assignment, which you see in our first column. This leads to a greater ability to draw a causal conclusion and allows us to generalize our results to the population. Most experiments, however, fall in this corner where there is random assignment but no random sampling. We can make some causal conclusions about our sample, but they are not generalizable. Most observational studies fall into this upper right cell, where there is a random sampling but no random assignment because it is not an experiment. We can identify correlations but not causation. But our results are generalizable to the greater population, and this is very useful. And finally, the types of studies we would like to help you avoid, except when necessary, very exploratory, are in this bottom right cell. There is no random sampling and no random assignment. Therefore, we can only make correlational conclusions for the sample and not the population. Again, this might be appropriate for some specific types of studies, pilots or user testing, but we do not want to spend resources drawing conclusions for only a small sample. Try to achieve random sampling so that even your exploratory studies are representative. In summary, through observational and experimental studies, we gather information comprised of observations and variables contained in a data matrix. Data types include numeric and categorical data, and each of these are used for specific types of values and analyses. Explanatory variables are those that we believe affect a response variable, and confounders may affect this relationship. Random sampling, including simple random sampling, cluster sampling, stratified sampling, and multi-level sampling, is the only way to have study results that are representative of the population. Observational studies lead to understanding correlations and associations between variables, and experimental studies can lead to understanding causal relationships between variables. Final thoughts. Rigorous research starts with understanding your variables and observations, identifying explanatory and response variables, confounders or modifiers, obtaining a random sample when possible, and grouping and, with experiments, randomly assigning your participants to treatment and control groups. This sets you on a path to good research.